Hi everyone, my name is Roti Balogun. I'm here just to really give you a short 15 minutes summary of the fantastic work that a group of about 120 African engineers who participated in a pioneering Africa Industrial Internet postgraduate program developed by the African Leadership University and powered by GE between 2018 and 2020. They really spent some time creating capstone projects that really expatiated on the value of the digital twin, which really is a collection of digital data that represents a physical industrial asset. They created them across a range of industries, from wind turbines in the power industry to MRI machines in the healthcare industry, and did some really fabulous work. So listen in to their presentations over the next 15 minutes. First 5 minutes was for the 2018 graduates, the next 5 minutes for the 2019 graduates, and the last 5 minutes for the 2020 graduates. Really good work. We're really proud of them and enjoy the work they did.
This is a snapshot of the presentations from the AIIP graduates showing a project that they worked on during the 2-day intensive. It combines some of the work that they did with data science and digital twin, and this is a result of the work they did. First off, we had a team that came from Transnet, and they were working on a train coupler digital twin. The objective was to come up with a design for a pin that allows them to connect more wagons to a train. So longer trains would then generate more revenue. And goal was to find materials and pin sizes that would justify the shear stress or withhold the shear stresses based off of the wagons connected on the train. And with their models, machine learning model and digital twin, they were able to demonstrate that you can vary different parameters on the mass or radius of the pin and material, and eventually see the extremes at which point the coupler is decoupled. Recommendations for this were to change material and type, dimensions of the pin as well, or find an alternative material with higher strength properties. Intelligent Battery Charger is a project from another team from Transnet, and their problem statement involves the high number of locomotive battery failures on the transit locomotives, which occur sometimes even before a year is finished. And so the idea is to have an intelligent charger that has the adequate parameters of charging that will enable the lifecycle of the battery to be increased. They used machine learning to do this, and in the end, they came up with ideal conditions which have the lowest loss percentage possible for charging, the shortest time, which I'm shown here, and they're able to understand what parameters in terms of temperature and charge current to operate this at. Recommendations from this were to either use a smart thermal casing, which would then heat or cool the system up to the ideal conditions, or monitor every battery cells with temperature and voltage sensors. A team from GE worked on a heat exchanger digital twin, which is heat exchangers from MRI machines that cools the coil area. And for their project, they essentially showed that you can utilize the Internet of Things to connect multiple heat exchangers across multiple locations, and you can track it on a dashboard, and you can record the temperature of each of the exchangers and predict what trends you will see. So if one of them needs to be replaced, you can plan your resources, whether human or capital resources, to avoid failures or correct it quickly when it happens. Also from GE, CB, and Omoholo from transportation was showing a digital twin that looked at the profile to come up with an optimal mode profile that will allow them to have great travel on both a straight and curved profile. With this statement, they were able to test different parameters of the profile, and the result was that they can narrow down using digital twin and play around to figure out what profile works best. From GE as well, there's a case for a individual household wind turbine in South Africa, argument being that electricity for the consumer has continued to go up between 2008 to 2018. And so with a digital twin, you're able to visualize what the temperatures would be, what the wind parameters would be for different locations, and the consumer would be able to tell what power output to anticipate for their wind turbine. So the example here is in Cape Town. They were able to get out 500 watts. Now, this is not just the only application. You can have an application on a mobile phone or an app that shows the consumer what to expect given specific wind speed and trends in the location. For this one, we're seeing a problem case that involves drilling. So the problem with that they face in their work is that when they operate their drill strings, there's a lot of vibration in the actual lateral and torsional directions, which causes bend, twist off, and damaging of parts. There's a real picture. With their digital twin, they're able to apply machine learning models to allow them to discover or predict whether they'll have vibrations, and the result is they'll be able to cut down on non-productive time, cost, and replacement of damaged assets, and also distribute the resources properly so that they avoid downtime because it can amount to millions. Recommendations is to actually implement this digital twin in the real world. So the team wants to test this out, and they would require project sponsorship in order to do this because it would reduce the challenges they're facing now in industry with drilling vibration. Finally, we had the power generation efficiency team, which addresses the issue of microgrids being a solution to the standard grid, and generators is another area where a lot of people are taking it up, especially in countries like Nigeria. However, there's large variable cost to the consumer for the fuel and maintenance to run it. So they wanted to test for efficiency of their generators by minimizing specific fuel consumption. And to do this, they wanted to understand what parameters they needed to have in order to see the effect on specific fuel consumption. So this is the dials are moving because of the machine learning model that the team implemented. And they can also compare different generators, and they can track trends over time and predict inefficiency. Thank you.